So students, this is part 3 in the test review, and this question actually deals with why some groups are actually ortho-para-directing, so directs an incoming electrophile to the ortho position or para position when that group is already on the aromatic ring, and also shows you why it is so. How does it come about? Why does it direct to that particular position? So we're going to show you what happens when the group is on there to the molecule. We're going to draw some resonance structures and show you stabilities of some of the intermediates in this scenario, and maybe answer the question. So I'll go straight into it. Right, so the question says, by drawing resonance structures, explain why aniline directs an incoming electrophile to the ortho and para positions. So we know we have to draw some resonance structures to try and explain. We also need to use aniline as the example and not just any random example. We're going to show you as well how to pick groups at the ortho para position and then draw some resonance structures. So this is the structure of aniline. Remember, aniline has a lone pair on nitrogen, and this is all important because that lone pair can be directed toward the ring, and we can delocalize these electrons with these pi electrons on the aromatic ring. But the question asks you about directing an incoming electrophile, which means that another electrophile is going to come at the ortho and para positions. So I'll just do 1 to show you what happens if we have another electrophile. I'll maybe just take any electrophile. I'll take a methyl group here. Here's my NH2 group. And what happens when this particular intermediate results in a mechanism, you will see that you end up with a tetrahedral carbon here and a carbocation at the other carbon. So now we're going to look at this carbocation that we created here and see if we can come up with a stable structure, right? A structure that is more stable than others. So I can do exactly the same thing, right, by putting a group on the meta position. I'll put the same group on the meta position, and I can put a group on the para position. And if I put a group at the meta position, first I create a carbocation. Remember, hydrogen is still there, and I can also get a carbocation here. Remember, I have the hydrogen now there. So I can draw resonance structures for each of these by moving the hydrogens around, and I can show you how to do it in this first one. I can now take these electrons, put it toward that bond, and come up with a resonance structure. Like, say I didn't do anything to that, I moved that bond, positive charge is now there, I've taken electrons away from there, I have NH2, CH3, and that's a resonance structure for this one. I can draw another resonance structure for that one. I can now take electrons from here, I can get this type of structure. I've taken electrons away from this carbon atom, that becomes positive, and that's your resonance structure for here. I'll just do one for this. I can take that away from there. I can get a double bond there, a double bond there. This is now going to be positive, this carbon. So I can get various types of resonance structures, and there's many more that I can draw. I can draw different types here, and you'll find that there's 4 resonance structures that you can draw for this, and there's 4 resonance structures you can draw for this, and there's 3 resonance structures you can draw for this. Now I'm going to draw your attention to the fact of 2 resonance structures that's going to make these intermediates very stable. And remember I said that your lone pair on nitrogen can be donated toward your ring by resonance. So I can donate it in this fashion. And if I donate it in that fashion, what you find is that I have now a stable resonance structure. And I'll tell you why in a little bit. Let's just draw this resonance structure. You'll see now this nitrogen takes on a positive charge because you take an electron away from it by the lone pair and direct it toward that carbon, share it between this lone pair between the nitrogen and the carbon. And now you'll notice in this particular structure that if I look at every carbon atom here, 1, 2, 3, 4, 5, 6, and even this carbon atom, all have a complete octet. It has 8 electrons around the carbon. So all have 4 bonds, each bond has 2 electrons, that's 8 electrons around the carbon. If I look at my nitrogen atom, although it's 1 electron short, right, in its valence shell, it should have 5, but it has now 4, 2 from this double bond and 1 each from the NH bonds. That makes it 4, so that's why it's got a positive charge. If I look at nitrogen more carefully, I've got 4 bonds to nitrogen, a complete octet. Right, so this particular resonance structure has a relatively stable carbocation intermediate because all the atoms have a complete octet. Right, so it's relatively stable because all your atoms have a complete octet. And I can do exactly the same thing for this structure. This lone pair can be donated toward the ring in that fashion. And if you look at this, 4 bonds to the nitrogen, 8 electrons around nitrogen, and 8 electrons around each of the carbon atoms. All the atoms in this also have a complete octet, so this structure is also relatively stable. And if you look at these types of compounds, I can only draw structures here with carbocations on the carbon atoms. There's no way that I can resonate or delocalize this lone pair with the aromatic ring and end up with a intermediate, which means that these, the ortho position and the para position, have a stabilized intermediate, which means that the chances of electrophilic aromatic substitution occurring at the ortho and para positions are now highly likely.